So, the multiple choice, your first attempt on the multiple choice has to be on Monday. The second attempt will be due by that Friday. And then Wednesday will be the free response. Huh? Yeah. And I've already kind of shown, hey, look, here are 3 things. Here, look, I've shown you what the last test, what the free responses look like.
What's about like rectangle number 3? That's the railgun.
No, oh, the railgun at number 3?
No, that's number 2.
Oh, it's a loop above a wire with a current.
Oh, wait, this doesn't include everything. This is last minute stuff.
This is just this unit stuff. So there's going to be an LR circuit on question number 4. We did LRs last class, right? There's going to be an LC circuit today that we're going over today. That's going to be question 1. There's going to be a loop above a wire, which you do not use Beelzebub's law for a wire. Use Ampere's law to get mu I over 2 pi d. And then integrate, it's the integrating that loop thing. That's a question they really like for some reason, because most people don't know how to do it. And then number 3 is going to be a rod being pulled. Basically, it's a railgun. It's a railgun problem. All right, so here we go. We're going to go very quick. Hey, remember back in Physics 1?
No.
There's a mass on a spring, right? The good old days, right? We have a mass on a spring. And I told you in Physics 1 that the minus symbol in front of kx for Hooke's law is only important in Physics C. It's now that day. And what ends up happening is that any time you end up with an equation that looks like this, it is always going to produce a sinusoid. And it has to have the negative symbol in the front of it. All right?
Sine, and we get like a sine x, and then derivative of like. Can you derive it to a sine equation?
Huh?
Can you derive it to a sine equation?
You want me to derive it into a sine equation?
Yeah.
You got it. Look, I derived it. Look, if I take this function, and I take its derivative, I put a w in front. I take the derivative of it again, I get a second w in front. And what ends up happening is this is something that's called angular frequency. And your angular frequency, there is these relationships between your max velocity and your max acceleration. And we know this because if you take the derivative of these functions, you get these w's in front. Or they're actually called omegas, right? And those are good relationships to know. Those are really good relationships to know. Because how do I get what omega is? Well, if I plug these derivatives that I just did into the original equation, am I going too fast? Are we all good on this?
No, you can go faster.
I can go fast, you got it?
No.
If we plug these equations into the original equations that we wrote earlier, what we discover is omega equals something called the root k over m.
Oh, yeah, that.
So the goal of the entire, so the goal will always be to write a function that looks like negative x m over k d squared x over dt squared. The goal is always to write some function that looks like this, because guess what's in the brown box? Omega squared. That is the goal for today, is to write this function. And we will know that this is omega squared. That's the goal. Because the AP test, they don't expect you actually to derive this. The goal is to go and write it into this form and recognize that that is omega squared. So it's going to show up in a lot of different ways. All right, the last thing I want to talk about is the energy. So this thing has an energy, right, which is kinetic energy plus potential energy, right? And you guys know that we can plug in our function for x. We can plug in our function for v, right? And hopefully you guys remember, in the very end, if we plug in the function for both of these, and I simplify it down, it reduces down to 1/2 a squared, where what's a again? The amplitude squared. It also equals 1/2 the mass times your maximum velocity squared. Right? We all good on that, right? And that all makes sense, right? Because when it has max velocity, there is no potential energy. When it has maximum potential energy, it has no velocity. All right? So these are all stuff from Physics 1, right? So nothing crazy so far, right? All right. Simple pendulum. So we have a simple pendulum. What is the restoring force for a simple pendulum in this case? It is mg, but it's the sine component of mg. So what we have to do is we have to start with the rotational version of Newton's second law, which is, if you guys remember, the sum of torques equals I times alpha. Right? Now the torque that's going to be involved is just going to equal mg L sine of theta. Why do I have to put the L there? It's so, remember, torque is a force times a lever arm. In this case, our lever arm is L. The moment of inertia for a point particle moving in a circle is just mL squared, right? Because moment of inertia is just mr squared, right? And then we have alpha, which is d squared theta over dt squared, right? And hey, what cancels out, team? One of the L's cancels out, and the M. And oh no, team. Oh no. And this should have a negative in front because I always lose. Guys, I'm going to be very honest with you. I always lose the negatives when I do this. So if I just throw a random negative on there, that's just because you have a bad teacher and I would fail Mr. Decker's class. Okay? Don't tell Mr. Decker if I just throw random negatives because I know what the answer should be. And hey, we got a problem, guys. This does not look like the equation we just wrote, right? But wait a second. Y'all are learning about Taylor expansions, right?
No.
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 And what is the highest order term for the Taylor expansion of sine?
It's like x to the x.
It's just x to the 1
Yeah.
over 1. So if we ignore all higher order terms, we pick the smallest order term of sine, we end up with is something that is called g over L times theta, which actually I'm going to go and put, I messed up. Just going to put right here, theta minus is equal to L over G, d theta squared over dt squared, right?
Oh, yay.
Hey, wait a second. Does that look like what we just talked about? What's in the box, guys? Box is
Omega squared.
omega squared. Now you're probably wondering, like, why can I do that, Mr. Seals? Because guess what? In math, that sine right there, our terms for sine is equal to approximately our first term, which is theta, minus theta to the third power over, I think it's n, so it's into 3, right? So this is going to be divided by 6, right?
It's 3 factorial. Yeah.
3 factorial, right?
Guess who's gonna be at
plus
Deckers
theta.
after
So
school?
this is why we call it a small angle approximation, because as long as it's a very small angle, a small number to the third power is practically zero. And the next term would be a small number to the fifth power, which is even closer to zero.
So this is how I know I'm in a physics class.
Huh?
This is how I know we're in a physics class.
It's like
Oh, this one's dangerous.
Yeah.
like you just take the derivative at zero. What?
Yeah.
Yeah.
Okay. Oh man, you guys were like, wait, why did you have to bust out the Taylor series, Mr. Seals? Why did you have to bust that out of all places?
Only the BC kid
I barely know what
like,
Okay.
Do you want to come with me after school? I have a test today. Oh.
And hey, as once you guys know omega, we have the equation that omega is equal to 2 pi over t, and this is where this equation came from. Okay. Those of you taking mechanics test, you guys were asking about, hey, what is a physical pendulum?
Yo, I haven't started studying for that.
Okay, well, don't worry, I'm going to help you start today.
Absolutely.
I like how you mentioned we know Taylor series, Mr. Seals, even though we literally have a test over that today.
Huh?
We have a test.
You have a test over Taylor series today? Oh, man, okay. Okay. Basically, in a physical pendulum, the center of mass is not located at the center. It's located somewhere up here, right? So, I'm going to go ahead and do the small angle approximation already. Is everyone okay with that? Because we'd have to do the same thing with the small angle. So, what our torque would be is mg. In this case, I'm going to call it, instead of L over 2, I'm going to call it a distance d times theta. The distance d is the distance to the center of the rod. It doesn't have to be L over 2. It could be any distance. Any distance. And this will equal the I times d theta dt squared, right? And I always forget the negative. There's a negative because it's a restoring force. I always forget that. You guys are going to see on the LC circuit, I'm going to forget the negative. I can already tell I'm going to forget it. Okay. Oh my gosh, guys, nothing cancels out, right? So we have to just write it out. So what we're left with is negative theta equals I over mgd. So, what's in the box, friends? That's going to be your omega squared. Hello, friend. Are you in Miss Patrick's? All right, can you come here because there are so many people who are testing right now. Are you on this page? Just tell me what page you are, and I'll fix it. All right, Miss Diamond? All right, nice to meet you, Miss Diamond. Just chill out.
That's
All right.
such a lovely name.
Huh?
That's a nice name.
There we go. All right. So this is how we get omega squared. Once you have omega squared, we get that the period, we end up getting our value. Here we go. Wait, it's 1 over omega squared. We get what omega is. Once we get omega, that's what our pendulum is, right? Actually, you know what? I've been messing you all up the entire time. Because what I've been putting it as, I've been putting it on the wrong side. Omega squared is going to go in front here. Oh, wait, that is omega squared. Wait, is this switched? Am I losing my mind? Hold on.
How is that equal to omega squared?
That's the physical one.
Because there's another equation where it's like this. What is it?
Oh, no, that's right. That is omega.
Because, wait,
It's not a physical
but this one's, I'm over 10.
Like the simple
Those
Yeah.
two over L, so you see 1 over omega.
Okay, L over G. Okay.
You don't have to work.
Sorry, it's whatever goes in front of the theta. Sorry, I got it swapped. My brain's not fundamentally working. All right. So sorry, guys, I messed up. I've been messing you up the entire time. what we want is negative box. I don't know, a symbol, star, equals d squared star over dt squared. We want to write it in this form, replacing star with something, and whatever goes in front of the first star, this right here is going to be omega. Sorry, I messed up. I told you guys omega squared. Sorry, I'm like, my brain is not functioning.
I feel like
My-
you call star u in calculus.
Sure, we can. You want? No, I don't want to do u because u is something else. Use potential energy.
Sure, it's not the u.
I guess we could do little u.
Yeah.
Like usually like little u.
Okay, there we go.
Because it's a substitute.
You don't
we
really
usually
use
use u.
u.
That's-
Okay, so we'll do a little u. A little u. Hello, friend.
Do you have a student?
Huh?
Do you have a student?
I do have Andrew.
Perfect, thank you.
Andrew, you've been summoned.
Okay.
Sweet 4. All right. Sorry, I'm kind of going fast. So hey, let's talk about LC circuits real quick. You're probably wondering, like, this is an E&M class. Why are we talking about mechanics? Well, what ends up happening is you initially charge your capacitor. So your charge is in an unequilibrium state. So your charge will be located, you'll have a positive charge on one side of your plate and no current at the beginning. And suddenly, this charge is going to try to go back and neutralize the other side, right? But there is an inductor that will try to maintain the current while it passes through it. So wait a second. It ends up creating these sinusoids, which is kind of interesting because what's great about this is that how is current and charge related? So I equals dq dt. The same way that velocity is the same thing as dx dt.
That's convenient.
But yeah, it is convenient.
It's the derivative of current.
Which means if we do Kirchhoff's loop rule, we end up getting a situation where we get the exact same equation we got last time, which is, actually I'm not even going to drive it, I'm just going to go and put it on here because I keep screwing it up, is that your omega squared ends up equaling 1 over LC. So how do I get a period from omega? Well, your period will end up equaling 2 pi times the square root of LC.
What's the period even mean situation?
The period? Well, notice the current is sinusoidal. Guess what the period is? The period is the time, I'm going the wrong way. The period is the time for it to repeat itself, both in the current and in the charge on the plates.
So like one entire loop, or
Huh?
like one loop around the circuit, or what is it? Like
So what ends up happening is these charges go through and try to neutralize. But because there is a current, when these things finally neutralize, this inductor will keep pushing the current through the circuit. So it will cause them to be in balance again. And if they're unbalanced, guess what's going to happen? They're going to try to neutralize again, but the inductor will maintain that current and they'll get out of balance. So this LC circuit will create a or as long as there's no damping, but if you put a resistor in here, there's a damping, so it actually goes and it dampens over time.
So it's a
Yeah, I know, but we don't go and do that. We don't call it, there is no RLC circuits where you would have damping waves.
so you have to use an e to the negative x.
Yeah, okay, shh, yes, I know. Well, we'd add an e to the negative x, or an e to the negative t, if there was a resistor in here.
That makes sense, actually. I was thinking about it.
Yeah,
It's always E.
which actually, the time constant what would the time constant be? I need to look up the time constant if you have an RLC circuit. Because I'm curious on what would happen. Because I would think the resistance would affect it, but the resistance changes the, whatever. We're going off track. We're going off track. We don't, I don't have an inductor. Sorry. If I had inductors, I could. Okay, you would not be able to buy a big enough inductor so we can see the effect. I would have to have an inductor and oscilloscopes. I don't have any oscilloscopes.
To notice what, sorry? I don't hear.
Basically, the time constants for RLC circuits end up being like this period ends up being in like kilohertz, 1,000 times a second. Yeah.
So it's basically in power supply.
Huh?
In power supply.
If there's no resistance.
Yes, it keeps cycling.
Actually, the crazy thing is if you make an LC circuit and you just point it at the sky, it will randomly start creating these sinusoids. Because there are so many random EM waves out in the universe right now, if you hold them up in the sky, they will start to oscillate because they would basically, an EM wave would hit the circuit, put a little current in it, and then it would drive the current from the airwaves. It's almost like in your car, there's probably an inductor with a capacitor that you can change the capacitance on, and it would change the frequency that they would resonate at. Yeah, it's your radio. Because notice there's a number on your radio, FM, a certain frequency, and you're changing the capacitance as you turn that radio, and you tune your radio to a certain frequency, and that frequency goes and produces sound being carried from the atmosphere. That's how radio works, guys.
Wow.
Okay, last thing I want to talk to you about. Last topic.
So every radio station is existing in the universe in the sky with all the sound.
Pretty much.
That's funny to think about.
There's actually, I would actually be kind of interested if there were aliens that could go and see radio waves, and they came to Earth and they were blinded by the amount of radio waves that are emanated everywhere.
Maybe
Like
that's why
every
we're not
cell
here.
phone is emitting a radio wave.
Can you feel the radio waves?
So if they could see radio waves, they could come to Earth and they would be just completely blinded because there would just be all colors in all directions.
Where's the people? We need to learn about other stuff here. All
right. Last thing I want to talk about. Last topic. Let's talk about energy. You know that the capacitor is charged with energy when you charge it when it's out of, when you charge a capacitor, you put it out of equilibrium, right? When charges move, they create currents, right? So when we look at an LC circuit, we have two types of energy. We have 1/2 Q squared over C plus 1/2 Li squared, right? But wait a second. This is a displacement. This is a movement. Think about a mass on a spring. What are the two energies that are there? You can think of your capacitors as potential energy. I understand they both have U in them, but you can also think of the inductor's energy as the kinetic energy of the circuit.
Kind of. I can kind of see it.
And if you notice, maximum potential energy is when kinetic energy equals 0. Maximum kinetic energy is when the potential energy equals 0. Just like before. Because you can look on the graph, where do we have maximum potential energies? What locations?
There.
Here, here, and here. Look at the velocities at each of those locations.
Zero.
They're all zero. Where do we have maximum
current.
kinetic energy?
No.
Here, here, and here. And what's the displacement of the charges at those locations?
Also zero.
Also zero.
Shouldn't they
is
be
the,
equal like amplitudes? Why is the
what's it
blue
called,
one
the
less?
insert and the,
I think it's like the, I think it's like the-
Because this is not an energy graph.
whoa.
Yeah, I think it's because like saying roll with it driving.
No, it's not even that. Like, okay, if we take these two things and set them equal to each other, guess what we get? We get Q equals to what?
Square root
LC squared times I.
So LC
I.
Because I is
times I, right? Oh, okay.
that LC is bending.
Okay. Cool. Hey, what's square root of LC?
Probably less than 1.
Isn't this omega?
Yeah.
Oh, yeah, that as well.
Actually, no, I messed up. I'm gonna put it on the other. Wait, is that right?
It's square root of 1 over
Hold on,
omega.
hold on. That's 1 over omega,
What if I just put
which
the
means I can
other
rewrite
place?
this as omega
What if I just
times
put
the
play
Q
on
initial
this? So I have
equals
what
I.
it's count for.
What is 1 over
Hey, what's I again?
X?
The velocity. What's Q again?
X. Well, in our metaphor, yes.
What's omega?
Omega is the amplitude.
Wait a second. What was the second slide that I said important relationships between max velocity and max acceleration?
dx.
Vmax is equal to omega times amplitude.
Oh, okay. And down here at the very end, what is the current equal to? At the very end, what is current equal to according to this equation? Current equals omega times your amplitude of your charge. This is going to be the max current. So it's almost like they're all related.
Is that an A or a Q?
That's a Q.
That's a Q, because normally we would write it as V equals omega times A.
Well, yeah.
Or V max.
Q
Max.
zero's A.
Q0 is A. I0 is max velocity.
In our analogy here.
Not an analogy, this is just the, but mathematically they're equivalent, yeah. In our analogy, yeah. All right, guys. Hey, I gotta go and post your quiz real quick. I'll get it posted if you guys want to go and start the review.